All right, let's see how this goes. I believe you should see me, and you should see some waves up there. Hello, everybody. It's good to be interacting with you in one way or another. I'm coming to you from home, where hopefully you are staying and heeding the advice of all the experts and keeping away from other people and big crowds and staying home. Try to slow down the spread of the virus here. Um, if you have any questions at all regarding the class, school in general, or you need anything, please reach out to me via email so that I can answer your questions as best I can and as honestly as I can. For most of you, you've known me for a long time, or you knew me this for only a few days, but I've always been pretty honest with you. So anything I can do to answer any questions you have, please let me know, and I will get back to you. I have what's called office hours. That's what we've come up with. The school administration's come up with. I'll be right in front of my email, 9:30 to 10:30, and then 2:30 to 3:30 every day. Now that doesn't mean I won't be checking my email or Google Classroom other times, but for sure during those 2 hours, 9:30 to 10:30, 2:30 to 3:30, I will be immediately available to answer your questions or emails you have. Um, what we're advised to do during this little transition time before we can move on with new material is to do review, remediation, and any uh, enrichment. So I thought we'd start today with a quick review of the two waves that we talked about before the coronavirus took over our lives and put everything on pause. And that were the two waves that I think you should see over here. I'm getting used to this whole camera thing. They were the longitudinal waves and transverse waves. The longitudinal wave looks like that slinky model we did. That's like a sound wave. And the areas where, if I don't want to be too loud in the mic here, but if I made a big sound, the sound, the air molecules would be compressed together. Okay, so that's called a compression. And you can think of all those air molecules being pushed together. If you were to hit a drum, strum a guitar, bang your hand, you would compress those air molecules together. The area where they're spread apart here, that's called a rarefaction. Okay, compression and rarefaction. You can measure the wavelength. You can either measure from compression to compression or rarefaction to rarefaction, and that will tell you the wavelength. Remember, in sound, the shorter the wavelength, the higher pitched it's going to be. The lower the wavelength, the lower it's going to be. The amplitude is measured by how high it is from the resting point. You can also look at how much the compressions are together for the amplitude, and that's how much energy is going into it. And remember, anything that the energy is going through is called a medium. So if it's the slinky or the air, that's the medium at which the energy is going through. In a longitudinal wave, the energy is going this way, left to right, would be going this way, and the medium is also going this way. So the medium and the energy are going in the same direction, and that's longitudinal. For a transverse wave, this is like that extension cord we did in the hallway or the classroom, or if you've done it outside with a garden hose. In fact, I was out doing some work, and Quinn was making some waves in a garden hose in the driveway. You can watch that garden hose travel. Here, the top of that wave, okay, this person, they shook that purple garden hose and it went up. The very top is called the crest, and that is how we measure the amplitude. The more energy you put into it, the higher it's going to go from the resting point, okay, wherever it was resting. So in Quinn's case the other day, he had it on the driveway, whipped it up. The resting point was the driveway. If we wanted to see the crest, the amplitude, we would have measured it from the driveway to the highest point in the air. You can measure the wavelength from crest to crest or from trough to trough. And you can measure the amplitude from the resting point to the trough. You could do that as well. All right. Now, in this case, the medium here, this purple line, let's say this is our purple extension cord, it is going up and down, and the energy is going this way. In a transverse wave, the energy and the medium go in opposite directions. So if you wiggle that garden hose left to right, the energy is going to be going this way. Okay, so they're going to go in different directions. I take a look at the Quizlet on our website, and I may as well pull it up here. Remember, to get to our website, you can go click on the waterfall, or go to pathway, and then go to pathways, and there's aerodynamic stuff that we did. And here is the wave Quizlet right there. And it has all that vocab on there and the pictures we did. And it also had the wave simulators, if you remember these. Okay. And you can send waves across based on that. And remember, you can change the tension on there. And then we had these waves here. All right. All right, that was a really brief wave review for today. Go ahead and look at that stuff. Tomorrow we're going to review the electromagnetic spectrum, the different waves we talked about. We put them around the board, the microwaves, infrared waves. Then we're going to go into seismic waves and earthquakes, because that's pretty cool. And that's where you can tell what the inside of the planet looks like. That's how we know what the inside of our planet looks like, by studying seismic waves. We've never been to the inside of our planet, but we know what it looks like based on how the seismic waves from earthquakes travel through it. And we can also get an idea of what other planets' cores look like, their inner layers, based on how waves travel through them. So pretty cool stuff there. All right, that's it for today, and I'll see you tomorrow with some more wave talk.